Hello all you calculus students. Here we are back again. Today's assignment 13. We're looking at section 4.1, talking about the chain rule. And as I've written here, we've learned how to differentiate x squared and sine x, for example. But how do we go about finding the derivative of sine of x squared? To do so, we need what's known as the chain rule. And the chain rule allows us to take the derivative of the composition of two functions, such as the derivative of f of g of x. And that's what's really implied when we look at the sine of x squared. The inner function, in this case, what corresponds to g of x, is x squared, and what corresponds to the outer function, f of x, is sine of x. And so what we need to do now is come up with the rule that tells us how we take the derivative with respect to x of the composition of two functions. Okay, so here we will now develop the proof for the derivative of the composition of two functions. And hopefully it'll fit on this page. So we're looking for the derivative with respect to x of f of g of x. Got enough? Maybe one more. And that equals, by the definition of the derivative, the limit as h goes to 0 of f of g of x plus h minus f of g of x all over h. Let me clean this up a little bit. There we go. Okay, so what can we do here? What kind of trick can we apply here so that we can get an idea of what this derivative is? And there is a trick. And the trick is to rewrite this as the limit as h goes to 0 of f of g of x plus h minus f of g of x all over g of x plus h minus g of x times g of x plus h minus g of x over h. Yeah, let's put in some big brackets here. Okay, so let's talk about this and what we have actually done here. What we've added is this little chunk and this little chunk. And really what we've done, essentially, mathematically, algebraically, is multiplied by 1. G of x plus h minus g of x over g of x plus h minus g of x. So we haven't changed the form of the original one, but we've made it something that we can now talk about. Because when we look at this expression right here, what that gives us is the, well, secant line joining the points f of g of x plus h. Well, let me say that again. Joining the points g of x plus h, comma, f of g of x plus h, and g of x, comma, f of g of x. So it takes a little thinking, but what this represents as a limit as h goes to 0 is the derivative of f at the point g of x. And when we look at this last part, that's a lot simpler to see. That's simply the limit as h goes to 0 of g of x plus h minus g of x over h, and that's simply going to be the derivative of g at x. So the really confusing part here is this g of x. And what we're doing is really evaluating f at g of x and evaluating f at g of x plus h and dividing by the difference of those two. So it's really the slope of the tangent line to f at g of x, which is exactly what this says. And this is the chain rule, and it tells us how to take the derivative of any composition of two functions. So we'll move on now and look at some examples. Okay, so here I have restated the chain rule, and what we'll do is we'll use it to take the derivative of sine of x squared. And the way I like to think of the chain rule is as opening up an onion, going layer by layer. Each time you open up a layer, you leave the rest alone. So if you look back here, what we do when we're taking the derivative of f of g of x is we take the derivative of f, but we leave g of x alone, and then we go in one layer and we take the derivative of g. So when I'm taking the derivative of the sine of x squared, I'm going to take the derivative of sine, leave x squared alone, and then take the derivative of x squared. You get it? So the derivative of sine is cos, I leave the rest alone, and then I take the derivative of x squared, which is 2x. And there we are. That's the derivative of the sine of x squared. So let's look at the next example. Here we're taking the derivative with respect to x of the cosine of tan x. Cosine is the outer function, tan of x is the inner function. So I take the derivative of cosine, which is minus sine, leave the inside alone, and then I take the derivative of the inside, which is sec squared of x. And there we are. Not so bad. So we know that there are plenty of times when we're looking at a function which is actually the composition of more than two functions. And the chain rule helps us here, and in fact we can understand how it would work for any multiple composition of functions. So in this case we're looking at the derivative with respect to x of the composition of three functions. And the language, the concept is the same as was described previously. We work outside in. We take the derivative of f and leave everything else alone. Then we take the derivative of g, leave everything else alone, and finally we take the derivative of h. And so what it looks like is this. The derivative of f, this stays the same, one more, times the derivative of g, h of x remains alone, and then finally we take the derivative of h of x. So it looks a lot like the chain rule with just two functions. So let's see if we can look at an example. So in this case we see we're taking the derivative of three functions put together. Sine is the outermost function, and then tan, and then the innermost function is 3t squared minus 5. And so when we take the derivative, we take the derivative of the outermost function and leave everything else alone. So inside stays the same. Okay, that's one layer of the onion. Now we're taking the derivative of tan, which is sec squared of 3t squared minus 5. And then finally we're at the innermost function, 3t squared minus 5, and its derivative is 6t. So take a second and think about that, and that's about how hard it can get. And so finally, let's take a look at what we call the extended power rule. And this is a special case of a function itself raised to a power. And if we think about a function raised to a power, the outermost function would be x to the n, and the innermost function would be f of x. And so the derivative of this looks a lot like the power rule. It's going to be n times f of x to the n minus 1 times the derivative of f of x. So as a simple example of this, let's think about taking the derivative with respect to x of sine to the 5th of x. It's going to be 5 times sine to the 4th of x times the derivative of sine, which is the innermost function, which is cosine of x. And so that shows us how we can use the chain rule to develop the extended power rule. It's probably worth noting in passing that the chain rule is probably the most widely used rule for differentiation that we're going to use throughout the course. And so there you go. See you next time.